Hi everyone. So I'm getting ready to talk about the pole flip, and I keep talking about the pole flip, and I'm not talking about the pole flip yet. But before I get there, um, keep talking about this. What's going to happen when we get caught in between these two larger potentials? If we take Pangea Earth and we start with this and we throw the moon at this, and if we somehow end up with this, and then I was explaining how my attention got alerted to down here, but before I get there, I'm going to go back here and talk about this and why I feel it's not only the concept of the spark gap that we have to consider here, it is this concept of a salt bridge that I was made aware of when I was learning some of the physics, or an ion bridge. And there's actually, I'll come over here to a video. Why is salt water conductive? Is this pretty much what's going on here? Normally, for those of you unaware, pure water is not a good conductor. It says it up here, but salt water is, and we're going to talk about why that is right down here. This is actually a pretty good article. I'm not going to I'm going to block that. This is a pretty good article about, I can't complain here for the most part. I was bashing the other article. This one I like. First, to understand why salt water conducts electricity, we first have to understand what electricity is, or something like that. Okay, electricity is a steady flow of electrons or electrically charged particles through a substance. Now, omit this part right here and just understand this. Electricity is a steady flow of electrons or electrically charged particles. That's really all electricity is. And I don't think people understand that. We're going to talk more about it. So, it's talking here about ions. And sometimes the salt bridge is referred to as an ion bridge, for those unaware. I'm going to link this article. Pure water, not a very good conductor. But when the salt ions, or sodium chloride, is dissolved in it, however, and then it explains, you get two pieces. One of these becomes positive and the other is negative. So there's a charge separation, and electricity is the flow of charged particles. But also what's happening here, you have a distance where the electricity wants to flow, but if you don't have something in between, if this is resistive, it's going to stop the flow of the current. There's nothing to conduct the flow properly. But if you have a salt bridge, that's what we're learning about, you can actually bridge the gap. They talk about you have two terminals, a negative and a positive, and then you go over to the earth, come over here, scroll out, and that's what you got. You got like one terminal up here and one would be fixated down here for frame of reference. And this is all salt water, why we should probably talk about that, because it's not just that, it's how this matter is going to respond to the force. And I'm all fine with that. And it keeps going. Why do ionic compounds conduct electricity in water? I think this might be an entirely different article, but it's still pretty good. The only thing that I had a serious problem with, Now they're talking about the difference between these. I'm going to get into chemistry too, because I really like chemistry and understanding how the force applies to it. A long time ago, my teacher, my chemistry teacher, actually explained why she thought everything was the electromagnetic force, and I was really young. I had no idea what she was talking about, but her words kind of resonated profoundly with me as I'm going through all this. And she actually said how she would lose her job if she explained some of these things, because it's outside of the realm of what they want kids to learn in school. The only thing I really had a problem with is when they're saying that this can be a function of temperature. Yeah, when it's like melted under a higher temperature, which has the... So this becomes important. You got to know how these things are in a different state. And we're going to watch this real quick about how fire can bridge a spark gap, or at least some of this.
What is a candle flame really made of? I'm at the Palace of Discovery in Paris to do an experiment that beautifully demonstrates the answer.
Alright, we're going to fast forward a little bit.
Okay, so we're turning
I'll
on an
link
electric
this.
field here. You can see that the flame is spreading out. Quel est le voltage ici?
Il doit être à peu près 20 000.
20 000.
On voit bien que papillon ou non? Oui.
Papillon?
The electricity is already
Oui, oui,
reacting on the fire. Fire is a
very cute.
plasma,
It's like a
which makes it
butterfly.
electric.
Alors la flamme, c'est un plasma. C'est un milieu totalement ionisé.
And you can see that the flame has two separate pieces to it now. One is going towards the negative plate, and those would be the positive ions, and the negative ions will be going towards a positively charged plate. So we see the flame kind of flattening out. But if that didn't convince you that a flame contains ions, then check out part 2 of our experiment, where we compare the conductivity of a flame to the conductivity of air, which is normally a pretty good insulator.
Now this is really cool.
It requires about 10,000 volts to break down a centimeter of air. So right now, this plate is at about 10,000 volts. You see that the spark is only a little. But if I put it around the flame, we'll see if we can get a bigger spark to happen.
Watch.
Look at that. Yeah. Because the flame has those ions in it, it means that we can break down a greater distance of air because there's greater conductivity. Yeah. That's awesome. You love doing this, right? Yeah. A strong enough electric field can actually extinguish the flame. But watch carefully what happens when the flame goes out.
Regarde.
Wait.
On voit très bien.
Now I'm not going to play the rest of it, but like you see these are the ions being carried this way and this is being carried this way. But the point was going back to where he's bridging the gap. He's bridging the spark gap very... I want to see one with... Give me a shot with the electricity, bud. We'll find one. But where he's bridging the gap, come back over here and see how much larger it was just by putting the flame in the middle. And then you got to figure all of this was taking place when we threw the moon at... There you are. This. So if throwing the moon at this started as a catalyst, fractured some of this, there's already an electric discharge being... Because you go back to the orbit, this is coming around here, and then this is coming around here, and at some point they're going to get to a point where the distance between the two worlds, there's probably going to be an arc, but then when you figure there's going to be already the arc here, and then you come back to your orbits, and you're looking at this, and this is one potential, and this is another potential, and then you're coming over here, and you realize that, yeah, okay, salt water is conductive, and then you come over to the Earth, and you realize all of this is salt water, apparently, and then you have this right here, and it's coming in from this side, like they're pulling in, they need ions to do this. Because there's the need to balance the charge between these two larger potentials, and the distance might be too great, but if you put Earth in the center right here, it kind of acts like the flame, in my opinion. But that acts as a catalyst. I like this article. If you can learn stuff, we're going to talk more about him later. But if you can learn stuff, it's good in my book. And when I was learning some of these concepts, the salt bridge definitely jumped out at me. Seeing stuff like this, yeah, it is awesome. But then when you're applying it to this scale, it's kind of scary. But if you come back and you think this is a remote event in the past, and if this is a remote event in the past, then there's really not a likely chance that this is going to happen again in the future. And then you come over to here, this potential is nowhere near, this potential is nowhere near, and you come over here, there's no more need to balance the charge, because now when we look at this, we already have our moon, so nothing else. To me, I don't see there's anything we need to be afraid of. Like, I find it fascinating that there's even a chance to prevent a head-on collision with the moon simply by applying classic physics and the physics behind the force. The force is obviously present here in this equation, so yeah, we'll talk more later, and maybe I'll explain the pole flip sometime today. Alright, take care everyone. Bye-bye.